If a body is put into a fluid, either liquid or a gas, it will experience a force upward. This is the reason ice floats on the top of water and a balloon filled with helium rises in air. This force is called buoyant force. If we define the gravitational force in the negative direction, a submerged object will rise in the fluid if the net force is positive, as in the case of the ice and the balloon, and sink if it is negative, like a rock in a pond. What is the reason for the buoyant force? It arises from the fact that fluid pressure increases with depth, and that pressure is exerted in all directions. By definition, pressure is force divided by area. In a static fluid, this pressure arises from the weight of the fluid, as shown here. However, in the case of fluids, it is convenient to express physical variables in terms of density and volume, rather than mass. This is what we have done now. Dividing the volume by the area, it follows that the pressure depends only on the height or depth of the fluid. So, if the pressure at the bottom of an object is greater than the pressure on top, there is a net upward force. The water ball at left is exactly supported by the difference in pressure. Because the solid object at right experiences exactly the same pressure environment, the buoyant force on the solid object is equal to the weight of the water displaced. This is known as Archimedes' principle. It follows that, no matter the material, bodies of equal volumes will experience equal buoyant forces. In this example, the balls of cork, aluminium, and lead will have the same volume, and hence they will displace the same volume of water, thus feeling the same buoyant force. However, the behavior of the three balls will certainly be different. The cork will bob up, the aluminium will sink, and the lead will sink more rapidly. The reason is the different weight of the three, and how it compares with the buoyant force. In the case of the cork, its weight is smaller than the buoyant force, while for the other two the weight is bigger. Archimedes' principle can be used to determine the density of the object submerged, regardless of its shape. We only have to compare the mass of the object with its separate mass when it is underwater. The difference is the mass of water displaced, which is responsible for the buoyant force. Knowing the density of water, 1000 kilograms per cubic meter, we can immediately calculate the volume of displaced water, which equals the volume of the object, and use it with its mass to obtain the object's density. Similarly, we can determine the density of any fluid if both the mass and volume of the object submerged are known. But let's get back to buoyancy. As said before, for an object to float in a fluid, the net force acting on it must be positive. That is, the buoyant force must be greater or equal to the object's weight. Expressing both forces in terms of density and volume, it immediately follows that the object will float if it is less dense than the fluid.